So 13.7 is where we are today. Tangent planes. And normal lines. All right. So we were talking last time. We've talked a little bit about a surface. If we have z, multivariable function z equals f of xy, the surface, and we have equals a constant, we get level curves. So this gives us level curves. And last time we talked about how the gradient is orthogonal to level curves, and then in the direction of the tangent vector to the level curve, so 90 degrees from the gradient, is the direction of zero change on our surface along the level curve. If we have a surface given by f of xyz, f of xyz equals a constant, we get level surfaces. So each constant gives us a different surface. We call these a level surface. So what we're going to do today is talk about surfaces in the form f of xyz equals some constant. And what we're going to do is we want to come up with a way. We said last time that so we can talk about tangent planes to surfaces like we talked about tangent lines to curves. So this is how we're going to go about that. So we have the surface f of xyz is a constant, and we're going to have a curve on the surface. So, and our curve is going to be a vector value function. So we're going to say r of t is, and this is going to be x of t I hat, y of t j hat, and z of t k hat is a curve on the surface. So just some curve. So what we're talking about here, just a quick sketch. So I'm not even going to draw my axes. So here's my surface, some surface, and I have r of t on this surface. So that curve is r of t. And this surface is the level surface f of xyz equals a constant. So we have a curve on the surface. So since the curve is on this surface, we can write that f of x of t, y of t, z of t is a constant, because that curve is on the surface. And we're going to use a chain rule to find the partial of f with respect to t. So we can say that the partial of f with respect to t is df dx times dx dt, just using our chain rule, plus the partial of f with respect to y. And I'm not going to do these. It's easy to write every derivative as a partial now. But x and y and z only depend on t. So we're going to write those as normal derivatives. There we go. Plus df dz dt. And this equals 0 because f of x, y, z is a constant. What is this quantity? So we have the f dx times the derivative of x with respect to t. We have partial of y with respect, partial of f with respect to y times the derivative of y with respect to t, partial of z with respect, partial of f with respect to z times dz dt. So we have this sum. This has to do with the x components. This has to do with the y components. This has to do with the z components. What sum do we have that has to do with the sums of the product of these components? What is it? It involves a gradient. It's kind of like a total differential, but not quite. This is a dot product. This is the dot product of del f dot, and what is the vector dx dt I, dy dt j, dz dt k? If r is x of ti, y of t, j, z of tk, that's going to be r prime. Del f dot r prime is 0. What does that tell us about the gradient and r prime? They are orthogonal. There's a 90-degree angle between them. Well, our position vector, was an arbitrary curve on the surface. Doesn't matter where it is. So this tells us that the gradient is normal to any tangent vector on the surface. Doesn't matter what our position vector is, it's going to be normal to any tangent vector. We picked an arbitrary position vector, and our gradient del f is normal to the tangent vector. This tells us that the gradient is normal to the surface, because I could draw any curve through a particular point, and the gradient is going to be normal to any of those curves. So our gradient is normal to the surface. So this is going to write down what we came up with. Del f is normal to r prime, and r is arbitrary. So del f is normal to the surface. What am I going to say? So our gradient is normal to our surface. So at any particular point, we can take the gradient, and it's going to be normal to our surface at that particular point. So questions about what we did here. So we have a surface, f of x, y, z is a constant. So we need our surface to be in that form, f of x, y, z is a constant. If we have our surface in that form, f of x, y, z is a constant, then the gradient, del f, is normal to our surface. So a couple of conditions here. So we're saying that we want del f at that particular point at a x0, y0, z0. We don't want that equal to 0, because if our gradient is equal to 0, then the dot product with any vector is 0. So we don't want our gradient to be 0. So if del f is not equal to 0 at that particular point, Del F is normal to the surface at the points x0, y0, z0. So this gives us a way to come up with a normal vector to our surface. So we want our gradient not to be 0. If that is the case, our gradient is normal to our surface at the point that we're interested in. This also means, just as a kind of a side note, that del F at, and I'm going to call this, I'm going to call that point P0, so I don't have to keep writing that. So del F at P0, at that particular point, is orthogonal to every tangent vector through that point. So our gradient is orthogonal to every tangent vector through that point. We're going to call the plane that is normal to del F at P0 is going to be our tangent plane at P0. So we're going to use del F, we're going to use our gradient as the normal vector to our tangent plane. So the gradient is normal to every tangent vector. So it's going to be normal to the tangent plane at that particular point. So this gives us a way to find our tangent plane. Del F gives us our normal vector, and it is normal to our tangent plane at P0. And we're going to call the line through P0 that is parallel to del F to our gradient at our point. We're going to call that the normal line. I'm going to say it's the normal line to F at our point. So we can talk about a tangent plane. Our gradient, del F, gives us our normal vector to our tangent plane at a particular point. So there's our point on our plane. Del F gives us our normal vector. And we can talk about our normal line. We have a point on the line, P0, and del F is our vector that's parallel to our line. So we can write our equations, parametric equations or symmetric equations for our line. So just another quick sketch of what we're talking about here. So here's my surface again. Here's my curve on the surface. We have a tangent vector to our surface. I'll do that in red. Make my little vector. So there's my tangent vector. So that's R prime. Our del F is our normal vector at that particular point. So there goes del F, normal to the surface. So there's P0 down here on the surface. And this curve is our r of t. And our surface is f of xyz equals 0. So at any point, our gradient is normal to our surface. Let me draw my little right angle there. There we go. There we go. So we have a way now of finding our normal vector. Normal vector gives us our tangent plane, gives us our normal line. So questions on this part, too. So the gradient, if we have z equals f of xy, our gradient gives us our direction, points in the direction of the maximum rate of change of the surface. If we have f of xyz is a constant, our gradient gives us a normal vector, a vector in space that is normal to our surface. All right, so let's use this idea. Let's use our gradient vector, to write the equation of our tangent plane. So our normal vector to our surface, we're going to say n. We can write it a couple ways. We'll see it written a couple ways. We can say it's the vector df dx, df dy, our gradient vector, df dz. We could also write it as the vector f sub x, f sub y, f sub z. Now, before we write our equation of our plane, if we have our surface, the equation of our surface, if we have z equals f of xy, we need our surface in the form f of xyz as a constant. So we rearrange this. We write f of xyz is just f of xy minus z, and that's going to equal 0. So I write my f of xyz as f of xy minus z, and then we have f of xyz equals a constant equals 0. And our normal vector then, for a surface in this form, our normal vector is going to be df dx, df dy, and -1. Or f sub x, f sub y, -1. So if we have our surface written as z equals f of xy, we rearrange it to look like this, f of xy minus z, to get f of xyz as a constant, equals 0, and then our normal vector becomes this. So the components of our normal vector give us our direction numbers for our plane, for our tangent plane. So the equation of the tangent plane to our surface, to f, at P0. P0 is our point on the plane, is going to be f sub x times x minus x0 plus f sub y times y minus y0 plus f sub z times z minus z0 equals 0. And we're evaluating our partials at P0. So this is our standard equation for our tangent plane at point P0. And if we have our surface written z equals f of xy, our tangent plane becomes f sub x, x minus x0, plus f sub y, y minus y0, minus z minus z0 equals 0. So these are going to be our equations for our tangent plane to the surface, depending on how we have our surface expressed. So a nice compact way of writing the equation of our tangent plane. Tangent planes will be very important. We'll use tangent planes for a lot of different things as we move forward. So that's why 2 years ago we invented the symbol for tangent plane, because we were saying tangent plane to f we were saying tangent plane to f constantly for different kinds of problems. And also remember that del f gives us it's normal to the surface, so we can write the equation of the normal line as well. The normal line goes through P0, and the gradient at P0, the gradient vector is parallel to the line. So we can write our equations, symmetric equations or parametric equations for our lines. All right, so now finally we can talk about tangent planes. All right, questions on this idea of the tangent plane to a surface. Now the places where I see, the most common place that I see mistakes when students are working with tangent planes is it's very easy to forget that we need our surface written as f of xyz equals a constant. So we have to write it in that form in order to use these equations for our plane. We have to write our surface as f of xyz equals a constant in order for our gradient vector to be normal to the surface. All right, so I have a couple of questions and then we'll do a couple of examples. And I think these next ones will be good practice just based on what I saw in the last quiz. So we want to describe the level surface for these examples. And we're going to say that we have f of xyz equals 0 for all of these. So we want to describe these surfaces. So for the first one, f of xyz equals 3x minus 5y plus 3z minus 15. So we want to describe the surface f of xyz equals 0. So what would that surface be? We're saying 3x minus 5y plus 3z minus 15 equals 0. So what is that surface? Let me rewrite it one more time. So what is that? Someone said it. This is a plane. Linear in x, y, and z. So this is a plane. Our normal vector is going to be 3, negative 5, 3. So this is a plane. So the level surface f of x, y, z here is a plane. All right. Next one, f of x, y, z equals x squared plus y squared plus z squared minus 25. And we're looking at the level surface f of x, y, z equals 0. So this is a sphere. And what's our radius? radius 5. So when I set this equal to 0, I get x squared plus y squared plus z squared equals 25. So this is a sphere radius 5. All right, this one, let's be careful with this one. 4x squared plus 9y squared minus 4z squared. And we want to describe this surface. F of x, y, z equals 0. So I'm going to write this. We're looking at the level surface. 4x squared plus 9y squared minus 4z squared equals 0. So what is that surface? It's going to have something, there's going to be something elliptical there, right? Because our numbers, our coefficients on x and y and z are the same. So we got the ellipse part, right?
Ellipsoid prism.
What is it? Elliptic hyperbola? Okay, let me rewrite it one more time. Let me rewrite it one more time. So I think some of us are seeing it. 4x squared plus 9y squared equals, on this level surface, equals 4z squared. So what is this? In the yz plane, so we're getting rid of this. 9y squared equals 4z squared. Take the square root of both sides. What do we get? 3y equals plus or minus 2z. What are those? Y equals 2z. That's a line. Do the same thing in the xz plane. 4x squared equals 4z squared. Take the square root of both sides. We get 2x equals plus or minus 2z. What are those? Lines. So in the xz plane and the yz plane, we get lines. Parallel to the xy plane, when z is a constant, we get our ellipse. 4x squared plus 9y squared equals a constant. So what is this? A cone. And what was your term? Ellipticone. So several of us said ellipticone. So we have an ellipse parallel to the xy plane when z is a constant, and the sides in the xy plane and the yz plane we have lines. So this is a cone. I think the cone is a surface that students confuse with other surfaces most often. This is the cone. All right, last one. And again, my hope is by the end of the semester that we look at these things and we say, oh, that's a cone. Oh, that's a sphere. Oh, that's a paraboloid. Not even have to think about it. 16x squared plus, or let's see, minus 9y squared plus 144z is our constant, or is our surface. And we're looking at f of x, y, z equals 0. So 16x squared minus 9y squared plus 144z equals 0. So what is that one going to be? Max says one of those paraboloid things. So in the yz plane, if we take this over to the other side, in the yz plane we have a 9y squared and 144z. What is that? Parabola. In the xz plane, 16x squared and 144z, another parabola. But then parallel to the xy plane, if z is constant, we have 16x squared minus 9y squared, which is hyperbolas. So we have parabolas and hyperbolas. So this is a hyperbolic paraboloid. Parabolic hyperboloid. They look like a saddle.
Oh.
So, like this, like that. It's hard to draw them. All right. So those are level surfaces. We're going to be doing a lot of work with surfaces, so it is important to be able to visualize these surfaces. All right, I want to do two examples. Let's see. Is that it? Two examples. Yeah.
You get a wrench.
All right, so want to do a couple of examples. So we want a unit normal vector to this surface z equals x cubed at the point 218. So we want a unit normal vector. What's the first thing we need to do here? We need the gradient, but we need to do something with our surface first. We need f of x, y, z equal to a constant before we take the gradient. So I'm going to say f equals x cubed minus z. So there's my surface. There's f of x, y, z equals a constant. And this equals 0. So when I subtract z from both sides, I get 0. And what gives us our normal vector? The gradient gives us our normal vector. So del f del f gives us our normal vector, so we take the gradient. Del f is going to be 3x squared I hat. We have no y component, so minus k hat. So there's our normal vector. We want it at this point, so del f at, and then let's call this so we don't have to write as much, p0. So del f at p0 is going to be, when we plug this in, we get 12i minus k. And we want a unit normal vector, so what do we need to do with our normal vector? We get a unit normal vector. Divide by the magnitude, so we normalize it. So we're going to normalize our vector. So we divide by the square root of, what do we get, 145. So our unit normal vector, n, is going to be del f over the magnitude of del f. And that's going to be 1 over the square root of 145 times 12i minus k. So that would be a unit normal vector at this particular point. Unit normal vector, something in chapter 15, we're going to be using, use unit normal vectors a lot. Chapter 15 is not all about, but we'll talk about surfaces and doing things with vectors and surfaces, all different kinds of things with vectors and surfaces. So we use the normal vector. One of the things we'll do in chapter 15 is we sum the normal vector over of a particular, the cross product with a vector field with the normal vector over an entire surface. So that's one of the things we do with the normal vector. We talk about this, we sum the tangent vector on a surface. We do lots of interesting things with our vectors. All right, questions on this example? Unit normal vector, something that we'll find a lot. All right, one more example that has to do with tangent planes and normal lines. So we want the equation of the tangent plane, and we want symmetric equations for the normal line to x squared minus y squared plus z squared equals 0 at the point 5, 13, negative 12. All right, so what's going to be our first step here? We want our tangent plane, we want our normal line. So what do we need? We need our normal vector. So we have to find the gradient. We need our normal vector, so del f. Just as a reminder, del f gives the normal vector. So we find our gradient. So del f, in this particular case, 2xi minus 2yj plus 2z. Okay? And at this particular point, at 5, 13, negative 12, we get the vector del f is going to be 10i minus 26j minus 24k. So there's our normal vector. Our normal vector gives us our direction numbers. Gives us our direction numbers for our tangent plane and our direction numbers for our normal line. So I'm going to say A equals 10, just to use the terminology that we used before. B equals negative 26. And C is negative 24. So now we're ready to write our equation for our plane. We have our point. We have our direction numbers. So the tangent plane x minus 5 minus 26 y minus 13 minus 24 z minus or z plus 12 equals 0. So there's our tangent plane. And our symmetric equations for our normal line. Do we remember how to write symmetric equations for our normal line? Symmetric equations. So to write symmetric equations, x minus x0 over a equals y minus y0 over b, and that equals z minus z0 over c. So we get x minus 5 over 10 equals y minus 13. I'm going to say negative y minus 13 over 26, and that equals negative z plus 12 over 24. So those are my symmetric equations for the normal line. How would we write if the problem asks us for parametric equations of the normal line? What would we do? Do we remember? Our parametric equations, what's the form of the parametric equation? X equals x0 plus at. Y equals y0 plus bt. And z equals z0 plus ct. So if we want a parametric equation, we get x equals 5 plus 10t, y equals 13 minus 26t, and z equals z0, negative 12 minus 24t. So those are symmetric equations, those are parametric equations. Do you remember how to write the vector equation for the line? So I'm just kind of compressing these equations. So that would be the vector equation. Or you could say r equals r0 plus t, and then we say this is v for our vector parallel. If ABC is our vector parallel. So that would be our vector equation. Normally this book likes to ask for the symmetric or the parametric equation, but it's good to know the vector equation. All right, questions? Questions on tangent planes and normal lines. We'll do a little bit more with tangent planes and normal lines tomorrow. We'll talk about finding the line parallel to or tangent to the curve of intersection of two different surfaces. That's one type of problem we'll talk about. That one's a fun one. All right, homework.